Good morning. Today I'm going to teach you about molecular geometry. And now that you know about bonding, this is going to involve molecules that are covalently bonded together. So you now know how to draw Lewis structures, and I'm going to teach you how to predict the shapes of those molecules based on how many atoms are bonded together and how many lone pairs are on the central atom. So before we begin, I want to tell you about a theory that all of this is based on. And it's called the VSEPR theory. Now, VSEPR is an acronym. It stands for Valence Shell Electron Pair Repulsion. So what this means is when you have a molecule, those atoms are going to want to get as far away from each other as possible. So for example, if you have a molecule of water, H2O, when you draw your Lewis structures, I've been pretty lenient about where you put your lone pairs. So you might have done something like this. And then when you draw your hydrogens, you might have them out to the side like this. But what really happens is, yes, those hydrogens want to get as far away from each other as possible, but they also are repelled by these lone pairs of electrons. So the real shape, if you wanted to draw your Lewis structure to reflect what shape is being formed, it would really look more like this, where you've got your hydrogen atoms as far away as they can be from each other, but they're also trying to get away from these lone pairs. So I just drew these circles around the lone pairs to show you that they are creating a lot of repulsion. Electrons are negative. They don't like to be around other negative charges. So that causes these outside atoms and their electrons to want to move away from the lone pairs. So just keep that in mind as we talk about all the different shapes today. I'm going to be teaching you 5 different shapes, and we're going to switch over to the slides for Unit 5. And I'll be going back and forth today between the slides and my document camera. So the first shape you need to know about is called linear. Linear is when you have one bond or 2 bonds. And if it's 2 bonds, then the atom that's in the middle, the central atom, has no lone pairs. So I'm going to give you some examples of these. You've got HCl, Br2, and CO2. So we'll look at those examples by drawing their Lewis structures. So we're talking about the linear shape. And HCl, hydrogen has 1 valence electron, chlorine has 7. So when you form that bond, you can see that the shape these 2 atoms are forming is just a straight line. Now I'm also going to be using models today to show you what these molecules look like. So this is also the type of model you'll be looking at in a lab you'll be doing tomorrow. But what this represents, these are 2 different atoms because they're 2 different colors, and they're joined together by a bond. So you can see that this molecule forms a straight line. So the other example, the second example you had is bromine bonded to another bromine. Those both have 7 valence electrons, and they're joined together by a single bond. So once again, you see that that forms the shape of a straight line. And for this model, I have 2 orange atoms just to show you that it's the same atom or the same element bonded together. So now what we need to compare and contrast is the polarity of these 2 molecules. When we learned about how to draw Lewis structures for covalent compounds, I told you that you have polar and non-polar types of covalent compounds. If something is polar, that means that one of the nonmetals is pulling more on the electrons than the other one. And in the case of HCl, that would be chlorine. Chlorine is going to have a slight negative charge. It's more electronegative than hydrogen. So all the electrons are kind of going over here, even though they're still sharing. So that would make hydrogen have a slight positive charge. And the fact that one side is slightly negative and one side is slightly positive, that makes this a polar molecule. Now with our two bromine atoms, both of them are the same. They have the same electronegativity, so they're going to be sharing their electrons equally. We're not going to have a slightly negative and a slightly positive charge. So this is a non-polar molecule. Now for the third example I gave you for linear, I told you it's CO2. So I'm going to give you some options for how to draw that. Carbon has 4 valence electrons. Each of your oxygens have 6. So you probably are drawing your molecule like this. But another way you can draw it to sort of clean it up and so that you can see that the shape is linear, you can draw it like this. And the way this is going to look using our models, whenever I have a double bond, I'm going to be using springs so you can see that there's 2 bonds between the 2 atoms. So one double bond here, one double bond here. Carbon's in the middle, oxygens are on the outside. And you can see that this molecule is still a straight line. All right, so oxygen is more electronegative than carbon. Remember, oxygen is closer to fluorine than carbon is. Fluorine is the most electronegative element, so that makes these oxygens slightly negative. And carbon is slightly positive. So we're going to see something a little different happen here. We're definitely calling this a polar bond. If you look at the bond between carbon and oxygen, this is slightly positive, this is slightly negative. That's what makes it polar. This is also a polar bond. Again, the bond between oxygen and carbon is polar. But if you look at the molecule as a whole, this side of the molecule is slightly negative, and the opposite side of the molecule is also slightly negative. So since both sides of the molecule are the same charge, the molecule itself is going to be nonpolar. So it is possible to have a nonpolar molecule that contains polar bonds. All right, so that's your very first shape. That is linear. Now we're going to switch back over to our slides, and I'm going to teach you the next shape. And this is just a reminder for linear. Those were the 3 examples I gave you. And for the molecular polarity, it's polar if the outside atoms are different. If they're the same, it's going to be nonpolar, like you saw with carbon dioxide. All right, so our second shape is called bent. What you're going to see with bent is it also involves 2 bonds, so not just one. Anytime you have only 1 bond, it's going to be linear. But if you have 2 bonds, and the central atom has either 1 or 2 lone pairs, then the shape is going to be bent. And the example I'm going to give you for that is water. I showed this to you earlier, but I'm going to draw it for you again. So bent is the shape we're looking at. The example is H2O. Now, if all oxygen had were 2 electrons, meaning that the hydrogens are still bonded to it, but if there were no lone pairs, those hydrogens would want to get on opposite sides of the oxygen. They would want to get as far away from each other as possible, and this would be a linear shape. But instead, as you know, oxygen does have 2 lone pairs, and that causes these hydrogens to want to get away from those lone pairs. So the real structure looks more like this. So instead of a straight line, we see the hydrogens bending away from the lone pairs, and that's why this shape is called bent. So the way I'll be showing you that, using our models, if you look at this molecule, you see that we have the central atom, that's oxygen in this example. You have your 2 hydrogens. Notice that they are bending away from the oxygen. And they're also bending away from those lone pairs. So if you see sticks with no atom on the end, that represents lone pairs. You'll need to keep that in mind when you do your molecular geometry lab tomorrow. So with the bent shape, oxygen is slightly negative, your hydrogens are slightly positive, and because of the presence of those lone pairs, that causes this molecule to not be symmetrical. So since one side of the molecule is negative, one side of the molecule is positive, this is a polar molecule. It is a polar molecule that contains polar bonds. Now you're going to see that anytime you have a bent shape. Bent is always going to have lone pairs on the central atom, and anytime there are lone pairs on the central atom, the molecule will be polar. So next to bent, I'm going to write always polar. And we'll switch back over to our slides. And you can see that that's the last note I've put on here for bent, is that it is always polar.